Hey everybody. So today what we will be talking about is antiderivatives. Before we start, antiderivatives, well, technically they're already something that you guys should be familiar with how to do. Um, it's just the same as a lot of the skills that you've been doing before, just in a different direction. So I guess today is when we start introducing a different direction into our normal calculus process of taking derivatives. So we'll start with this question. What are the four basic operations that we deal with in mathematics? And you know that I've asked this question before in a few lessons before this. They are addition and subtraction and multiplication and division. And the reason why I asked this question is because you know from experience that these operations aren't just separate entities, they are linked together. Addition is linked to subtraction in that addition, well, basically undoes subtraction and vice versa. And if they undo each other, it's almost like they're the same thing. Like we could rewrite addition as subtraction or vice versa. Um, like they're opposites, but a lot of times they almost act like the same thing. Multiplication and division work the same way. They undo each other, but any multiplication problem we could write as a division problem and vice versa. So again, they're almost the same thing. Now, what does this have to do with calculus? Well, you have learned an additional operation in this class so far. You have learned about this operation, which you should recognize as the derivative. And the derivative itself has an inverse operation as well that goes in the opposite direction. So much like numbers, if we were to start at 9, we could divide by 3, divide by 3, divide by 3. And if we wanted to get back to the starting point, we could multiply by 3, multiply by 3, multiply by 3. Just two different directions, but ultimately the same type of thing. And just like with multiplication and division, we can do this with the differentiation operator. If we started with 1/3 x cubed, you can imagine deriving that, getting x squared. You can imagine deriving that, getting 2x, and deriving that, getting 2. If we wanted to, we could antiderive, back up the chain, and get to something that's like 1/3 x cubed. That's a lot of what we'll be doing today, just sort of going backwards on the derivative rules that you already know. We'll be anti-deriving those derivative rules. So we have our first definition. Capital F of x is called an antiderivative of regular f of x if and only if capital F prime is equal to little f of x. And you guys should write this down. It's a fairly simple definition, and it's one that should make sense. An antiderivative is just a function that, when derived, gives you your original function, f of x. It should make sense. That's not to say it's something that's easy to find all the time, but it is something that we will be referencing. Now, what's interesting about this definition is the use of the word an. So notice that we used that word, not capital F of x is the antiderivative of f of x. And that's because there is no single antiderivative for any specific function. There's no single antiderivative for any specific function. So before I reveal the rest of this, take a second to think about why that is. Pause the video and think about why there might not be a single antiderivative for any specific function, why there might be multiple. Okie doke. So you should have seen or thought about that, like, if regular f of x is equal to 2x, then its antiderivative, big F of x, could be, well, it could be capital F of x equals x squared plus 2, because the derivative of this is just 2x again. We derive, we get 2x. Similarly with this, x squared minus 4 derived would also give us 2x. or x squared minus 3 pi, or x squared plus 102. All of these functions derived would give us 2x. But these are all different functions. They're not equal to each other, but they're all antiderivatives of the original f of x. Okay. In order to address this issue, we always state antiderivatives as follows. If f of x equals 2x, then the antiderivative is capital F of x, big F of x, equals x squared plus c. And that c right here really just stands for any number. It could be 3 pi, it could be 2, it could be negative 7, it could be 1.36 or 128. I think you get the picture. X squared plus c, where c is just a number. Because when we derive x squared plus c, differentiation destroys the number, and the derivative of x squared is just 2x. QED, antiderivative. Before we go on, we have a little bit of notation to discuss as well, so you guys are familiar with what you'll see afterwards. So this operation, called antidifferentiation, or finding the antiderivative, is also known as indefinite integration. So the antiderivative, otherwise known as an indefinite integral, is written like this down here. The antiderivative of little f of x is often denoted by, so we have big F of x equals, and then this is pronounced the integral of f of x dx, or the antiderivative of f of x dx. As a matter of fact, I'm going to write that off to the side here. So this means antiderivative. So the indefinite integral means the antiderivative. And it's called an indefinite integral because notice that we don't have any bounds right there, right there. It's not definite. It's not defined by bounds. It is indefinite, no bounds. So you can tell that when you see this, an integral sign without any bounds at all, you will be finding the antiderivative of this particular function inside. So before we go on, and in a second I'm going to ask you to pause the video, what I want you to think about is what would happen here. What is this statement equal to? So think about this for a second, pause the video, and we'll come back and take a look. Okay, so this is actually a very, might not look like it, but a very deep concept. This is, of course, the derivative operator. What it means is take the derivative of that thing. But, of course, this thing is already the antiderivative. It's the indefinite integral. It's the antiderivative. So the derivative, this is asking us to take the derivative of the antiderivative. It'll just undo everything. And, point of fact, it'll leave behind just regular f of x. The function that was inside the integral to begin with. The derivative of the antiderivative is just f of x. Again, should hopefully be fairly obvious, and it might not seem too deep, but it is something that we will be coming back to again and again and again and again and again and again and again. So, happy day. All right. Let's find antiderivatives for the following functions. Let's do some actual skills-based math here. So I've got this function right here, little f of x equals x squared. And we are interested in finding the antiderivative for it. Remember that that is often notated as capital F of x. Now the first thing that I want you to think about when antideriving is the power. The power should tell you everything you need to know to take the antiderivative at this stage. So if we start with x squared, we know that our antiderivative is going to need to incorporate x to the third power somehow. So capital F of x equals, and then we might need a number in front, so something to the third power. And then let's think about what this number could possibly be. Okay, well, I know that there's no number in front of the x squared, or rather the number is 1. So if I were to derive this as it stands, just x cubed, I'd get 3x squared. So if I were to derive that off to the side, I would get 3x squared. Now obviously here, we don't have a 3. So I don't really want that 3 to be there in the end. So I need to construct a number right here that would make that 3 cancel out. We don't want the 3 there. And that's why the number that we would put in front of this x cubed is 1/3. The 3 would come down in front, and 3 times 1/3 is just 1. And then the power reduces and becomes a square. Okay. And then always remember, antiderivatives always have a plus c at the end, because this could be any number. Okay. Take a second, take a look at these antiderivatives. Pause the video and see if you can figure them out right now. All right. So this antiderivative, so capital F of x, if we look at the same pattern from before, the first thing I do is I construct x to the 7th, because I know I'm anti-deriving, so I'm moving up a power. And then I know that the number 1 is in front of this, so I need to slap a 1/7 down there. Okay, and again, always remember plus c. The one over here, capital F of x, equals, so start with the same thing, x to the 4th, I move up to x to the 5th, and then I would want a 1/5 down in front of there if this were 1, but it's a 3. So what I'm going to do is I'm going to multiply 3 by 1/5, or basically just use the fraction 3/5 in front to make this happen. Because if I move this 5 down in front, 5 times 3/5, the 5s will cancel out. They'll cancel out, and I'll leave behind that 3, which we want. And again, plus c. For the last one right here, if little f of x equals cosine, then the antiderivative of cosine, it's just having us go backwards. So what function derived gives you cosine? It should just be sine. Sine of x plus c. Okay. So that leads us to this rule right excuse me, this rule right here. If f of x equals a times x to the n power, then the antiderivative is big F of x equals a over n plus 1 times x to the n plus 1 plus c. And what this is the reverse power rule. Because you move the power up 1 when you're anti-deriving, and then you would put the increased power down on the bottom in front of the x. Whereas with the regular power rule, we reduce it by 1 and multiply. Here, with the reverse power rule, we add 1 and then divide. Antiderivatives, at least at this stage, in a nutshell. Now, antiderivatives, I should say, they might seem very simple right now. However, they can get very complicated, especially when we start doing the anti-chain rule. There's also an anti-product rule, but it gets very deep. Just like division is harder to do than multiplication, antiderivatives are harder to perform than derivatives. All right. So let's just take a look at this example quick. If little f of x is 5x cubed plus 3x plus 2, finding the antiderivative is very natural to do. You just antiderive each part. See what you get. It's exactly what you would think. So I first do x to the 4th power, so I add 1. And then I slap the 4 underneath the coefficient. Okay, boom, antiderive that part. And then 3x, okay, so I'm moving x up by a power to x squared. And then I put the 2 underneath the 3, boom, antiderived. And then plus, and then the antiderivative is 2. It's so simple that it can be tricky, but really just what function derived gives you 2? Gotta be 2x. Boom, antiderived, plus c. All right, there we go. The antiderivative, just antideriving each individual part. At this point, I want you guys to try finding the antiderivatives of these. Remember your exponent rules for this one. Okay, pause the video and take a couple minutes to give it a shot. All right, let's take a look. So in this example, the antiderivative of little f of x should be, okay, so I move it up a power, and then the 3 over 3 would just end up being 1, so 1x cubed, or just x cubed. Let's try to do this all in one shot. So we have x squared, and then I put the 2 beneath the 4. 4 divided by 2 is just 2. And then minus 5, the antiderivative of 5 is 5x, because the derivative of 5x is just 5, and then plus c. All right, antiderivative. Now, for this function right here, what we are going to need to do is rewrite this first. So instead of 7 over x squared, and by the way, you can't just antiderive it like this looks. It's not going to be 7 over 1/3 x cubed. It didn't work for derivatives. It's not going to work for antiderivatives. In order to derive this, we needed to write it as 7x to the negative second in order for the power rule to work. Now for antideriving, we still want the power rule to work, so we need to write it with the power, and, well, put it up 1. So the antiderivative in this case, we'll take our power, and we will move it up 1. And up 1 from negative 2 is negative 1, not negative 2, or negative 3 rather. So our power plus 1 is negative 1, and then I put the negative 1 beneath the 7, and we would end up with 7 divided by negative 1, or negative 7, plus c. So our antiderivative ends up being negative 7 divided by x. That's x to the negative 1st power plus c. Okay, so let's just move on to some quirky examples that you could think of as being antiderivative related. You guys have done this skill before actually, so let's just briefly review it. I've got here the graph of the derivative f prime. So this graph is the graph of our slopes, because we're supposed to be graphing f of x from this graph right here, the graph of the derivative. So this graph tells us what the slopes are of our original function. I can see from this graph that I've got one slope of 0 at negative 1/2. So I'm going to make a slope of 0 at negative 1/2. I'll call this over here negative 1. And then we'll go 2 over. We'll call that negative 2. So and so forth. So I'm going to go by 2's here. So 1, 2, 3, yeah. So we've got slope of 0 from that, because that's where the derivative equals 0. So our original function, f, will have a slope of 0 at about negative 1/2. So I'm just going to draw a horizontal tangent line at negative 1/2. And then f is also going to have a slope of 0 at about 2.25. So that'd be about right there. So, I don't know, maybe I'll do something, maybe right there. Let's make it go up a little bit. Let's think about that. Now, let's think about what this graph might look like. Before this point right here, before the 0 slope, I can see that according to my derivative graph, I have positive slopes. So the graph of my original function should be traveling upward because of the positive slopes until we get to the 0 slope right there. And then I see negative slopes up until about 2.25. So it looks like I made a boo-boo here. I put my 0 slope above this one, when in actuality, my f of x has to decrease from negative 1/2 to 2.25 because I have negative slopes right here. So this is where f is decreasing. So let's erase this, and let's put it down here a little bit. That'll be fine. So then we'll make the function go down there, hit the 0 slope, and then it looks like our function hits positive slopes again over there, so boom, it's going to go right back up. F of x. Okay. You might also see this type of problem. It's called solve the initial value problem, and otherwise known as solve the differential equation. So what this essentially wants you to do is it wants you to find the original function. Find f of x. Whoop, sorry, not big f of x. Find little f of x, because we're working with the derivative here, such that when you plug in 1 into that function, you get 4. Notice that we start with the derivative here, f prime. So logically, in order to get to the original function, to move from f prime up to f of x, you need to antiderive. You might also see these problems written like this. Instead of f prime, you might see dy dx equals, and then 6x squared minus 4x. And then what we would do from here is we would just quite simply antiderive and see what we get. So the antiderivative of the derivative is just the function. We'll call it y. Or f of x, up to you. And then the antiderivative of 6x squared is going to end up giving us an x cubed, and then the 3 has to go beneath the 6, putting a 2 in front. So 6 divided by the 3 gives us 2, minus, so I see an x, so I go up to x squared, and then the 2 has to divide beneath the 4, so that 4 divided by 2 gives us another 2. And then always remember, whenever we antiderive, a plus c. Now, this, right now, just a little bit of vocab, is called the general solution. And what we want to do is find the specific solution that makes f of 1 equal 4 true. And this essentially means that, well, if x is 1, we want the function to be equal to 4. So if we want to find the value of c, the number specifically that makes this happen, well, let's plug in the values and see what c gets us that. So 4 would equal 2 times 1 cubed. Again, 4 is the y value, 1 is the x value. And we can see from this 2 times 1 minus 2 times 1 is 0. So all in all, we end up with c equals 4. Now this isn't the end. What we need to do with this is take that piece of information and now we write our specific solution that makes this true, which would be y equals 2x cubed minus 2x squared, and then instead of plus c, we found the specific number that makes the thing that we want to have happen, so we write 2x cubed minus 2x squared plus 4. Okay, and for our last thing, we have a little bit of a physics application. So it says a car is accelerating constantly according to the function a of t equals 4 meters per second squared. And the question that it immediately asks is, what is its velocity after 5 seconds if its initial velocity was v equals 10 meters per second? And this is another initial value problem. Hopefully you remember that in physics and how calculus relates to physics, or at least the kinematics part of physics, is that if we start with position and we derive down, we will get velocity. And then if we go one step further, if we derive velocity, we get acceleration. Now that is moving in one direction with derivatives. We now have the ability to move in multiple directions. So we can go from acceleration up to velocity, and from velocity up to position. So the way that we do this by moving up is by anti-deriving up from acceleration and anti-deriving up from velocity to get up to position if we need to. So I'm going to start with my acceleration function, which is a of t equals, well, simply 4. And then my velocity will be the antiderivative of that. The antiderivative of 4 is not 4x, 4t. And you can either write plus c, or you can either write plus v naught, because v naught means the initial velocity, v sub 0. And now what we have to do is use that initial velocity. That means at t equals 0, v equals 10. And if we plug in 0 for the t, and we plug in 10 for the v, we end up knowing that v naught, initial velocity, equals 10, which again should be kind of obvious. So v of t would end up being 4t plus 10. That is an equal sign. Let me try that again. That is a big eraser. Okay, there we go. So v of t equals 4t plus 10. And then the question asks us, what is the velocity after 5 seconds? So then we proceed to say, all right, v of 5 is 4 times 5, 20, plus 10. So the velocity after 5 seconds is 30 meters per second. Now for the position after 5 seconds, if its initial position was s equals -5, would work much the same way, except instead of anti-deriving from acceleration, we would anti-derive from our velocity function. So we would take that and we could anti-derive the velocity to get up to a nice position function. The antiderivative of v would end up being 2t squared, because the antiderivative of 4t is 2t squared, plus antiderivative of 10 is 10t, plus c, or initial position, s naught, s sub 0. And then initial position means the same thing here. So our full position function would be s of t equals 2t squared plus 10t minus 5. So the position after 5 seconds would be s of 5 equals, plugging in 5, so that's 2 times 25, which is 50, plus 10 times 5, which is 50, minus 5. So the position after 5 seconds would be 95 meters. All right. And that's pretty much it for antiderivatives. Remember that this video is on YouTube, and I tweeted it out, so you guys can watch this whenever if you need a little bit of a refresher for some of the examples. And all right. Thanks, guys. I hope antiderivatives go well.